Numerical exploration of the Riemann hypothesis using Turing's method and complex traces. Aaron Cattell. Abstract. This paper investigates the application of Turing's method and the argument principle to numerically verify the Riemann hypothesis, RH, up to a given height along the critical line. By combining zero-counting techniques with a visualization of the zeta function's image in the complex plane, we construct a multidimensional verification approach. We also introduce an animated complex trace of the zeta function as a geometric lens on the distribution of its zeros. Introduction. The Riemann hypothesis, RH, posits that all non-trivial zeros of the Riemann zeta function zeta s lie on the line res equals 1, 2. Turing's method, enhanced with the argument principle and visual trace analysis, enables us to numerically confirm this up to a certain height t. This paper combines these perspectives to explore the structure of the zeros both numerically and geometrically. Theoretical background. The number of non-trivial zeros with imaginary part between 0 and t is approximated by the Riemann von Mangold formula. N(t) equals t2 pi log t2 pi plus 7 8 plus s t plus 01 t, where s t relates to the argument of the zeta function. The Hardy z function z t equals ei t 1 2 plus it is real-valued and shares its zeros with zeta 1 2 plus it. Theoretical framework. 3.1 Argument principle and zero counting. The argument principle allows for counting zeros of meromorphic functions within a region by n(t) equals 1 pi arg 1 2 plus it plus correction terms. This provides a theoretical expectation for the number of zeros up to height t. 1. 3.2 Turing's method for verification. Turing's method confirms these zeros lie on the line by 1. Computing sign changes in z, t, across a fine grid. 2. Matching the count of those sign changes to n, t. 3. Ensuring consistency with theoretical expectations using Turing's bounds and intervals. 3.3 Complex trace visualization. The complex function trace gamma t equals 1 2 plus it can be visualized in C or lifted into R3 by plotting xt, yt, z, t equals 1/2 plus it 1/2 plus it, t. Every time this curve passes through the origin, it identifies a non-trivial zero on the critical line. This visual method connects geometry to number theory. Numerical implementation. Python was used to implement high-precision numerical evaluation of z, t, and trace zeta, 1/2 plus it. The number of sign changes of z, t, up to t equals 50 matched the expected number of zeros from the Riemann von Mangold formula. Visualization. We rendered the trace zeta, 1/2 plus it, as a 3D curve in R3, observing its motion through the complex plane. A sample animation demonstrates the dynamic behavior of the function and its tendency to spiral around the origin, signaling the presence of zeros. Conclusion. By combining analytic techniques, like the argument principle, and Turing's zero-counting method with numerical and visual tools, we validate the Riemann hypothesis up to a given height. This hybrid approach opens the door to higher verifications and deeper insights into the structure of the zeta function. References. E. C. Titchmarsh, The Theory of the Riemann Zeta Function, Oxford University Press. A. M. Odlyzko, Tables of Zeros of the Riemann Zeta Function, Online Archive. A. M. Turing, Some Calculations of the Riemann Zeta Function, 1953. G. H. Hardy, On the Zeros of the Zeta Function, Proc. Royal Society. 2. Figure 1.